Section 10.7 is power series. Now, what makes a power series is that each term in the series contains a power of x. X is a variable in the power series. So for example, here we have a power series centered at x equals 0 of this form where we have the sigma n equals 0 to infinity of c sub n x sub n. If we were to expand the terms, n is the variable of the power series, but x would end up being the variable of a polynomial. When we start with n equals 0, we would have c sub 0 times x to the 0 is 1, so we would just write our constant term, plus c sub 1 x to the first, plus c sub 2 x to the second, so forth and so on. And what it looks like is the terms of this power series look like an infinite termed polynomial. This would be a power series that's centered at 0, and if we had a power series centered about x equals a, it would take on this form. Notice that when we're centered about x equals a, we end up having x minus a raised to a power of n. This one was centered at 0. Well, if I wrote x minus 0, that's just x. So if you have the x raised to a power of n in your power series, that's going to be a power series centered at 0. And if you have x minus a in parentheses, then that would be a power series centered at a. If it was x plus a, where would this power series be centered? Negative a, because subtracting a negative is the same thing as adding. So when you expand the terms of a power series, you end up with what looks like an infinite polynomial. Like polynomials, power series can be added, subtracted, multiplied, differentiated, and integrated in order to get new power series. Now, multiplication and division are going to be really difficult with power series, but that doesn't mean that it's impossible. But addition, subtraction, differentiation, and integration are going to be fairly easy. What else do you notice about this power series? Doesn't this look a little bit like a geometric series? This is the terms of a geometric series. We have a times r to the n. This c here is just a constant. Now that constant may change as we expand out these terms, so that's why it's written as a variable, as a function of n. But this x to the n looks like it's in the position of our r to the n. What conditions were necessary in order for this geometric series to converge? The absolute value of r had to be less than 1. Well, the domain for this power series here would be that the absolute value of x is less than 1. So the domain for this power series would go from negative 1 to 1. That would be the domain on the polynomial function of x if I were to expand this out. For any power series, there are generally two questions we want to answer. The first one is, for what values of x does the series converge? And if the series converges, what function does that series converge to? If we have a power series that looks like this, let's not make this a sub n, let's just make this some initial value, a sub naught. If this is a power series, it looks an awful lot like a geometric series where a would be equal to 1 and r would be equal to x. This would converge to a over 1 minus x as long as the absolute value of x was less than 1. Because isn't this the sum of a geometric series? So the domain would be from negative 1 to 1 for this power series. And then we would want to know what function does it converge to? Well, it would be the sum of that geometric series. So here's the geometric power series for x. We have the sum n equals 0 to infinity of x to the n. If we were to expand this out by plugging in numbers for n, we would end up with this infinite polynomial equation that would be 1 plus x squared plus so forth and so on, x to the n, all the way out to infinity. This is a geometric series where the first term is 1 and the ratio is x. That converges to 1 over 1 minus x, so that would be the function that this power series converged to over this domain, because the absolute value of r has to be less than 1. So this would be the function that the series converged to. We call this domain of this series the interval of convergence. It's the range of values for which this infinite series is going to converge to the actual function. Let's look at this figure. It says the graphs of f of x equals 1 over 1 minus x is given right here. It's this blue graph. Y equals 1 over 1 minus x, which is what we said that our power series of x to the n converged to. That's that blue graph right there. We're expanding out the terms of this polynomial function. Our 0-degree polynomial would just be the constant function y equals 1. If we add another term, that would give us n equals 1. So then we would get a linear function, y sub 1 equals 1 plus x. So we notice that when this is centered at 0, all of these polynomial functions, if I expand them out, no matter what the degree, they are going to pass through that point at x equals 0. They're going to be the exact same value as the function and the polynomial. As I increase the value that I let n go to, I get a better and better approximation of this blue function right here. When n is equal to 1, I get y sub 1, and that's 1 plus x. That green line starts to approach the slope of this blue function right here. When y is equal to 2, I get a quadratic equation, 1 plus x squared, and now that curve is starting to approach the curve of the blue line a little better. And if I went out to an 8th degree polynomial, I would end up with this red function, and it does an even better job of approximating this blue graph right here, the one that we're interested in. If I let n go out to infinity, the infinite polynomial would be exactly equal to this blue graph right here, this blue curve, between -1 and 1. The infinite series is exactly equal to this function right here between -1 and 1. That's the way that a power series works. And you say, well, why would I want to use an infinite series to represent this rational function? Notice the terms of this infinite series, when I expand it out, form a polynomial. We like working with polynomials because they behave nicely. We can do more things with polynomial functions easier than we can with rational functions or any other transcendental function. So that's why we use power series. The domain of the power series gives us the interval of convergence. That's the range of values down here where our power series will be equal to the function. In this figure, we see a function. It's a graph of f of x equals 2 over x. That's this curve right here, y equals 2 over x. And then the first three polynomial approximations. So y sub 0 would be y equals 1. It's a constant function. Y sub 1 would be a linear function. It does a decent job of approximating it because it's starting to get the slope right here. And then the quadratic function, this gold function, does an even better job of approximating this function. If I were to expand this out, this function, using the polynomial expansion, first I would need to know what infinite series could represent this function. Well, I would want to be able to write it in this form. And I would like to have a be equal to 1 because that makes the arithmetic easier. And then the sum needs to be equal to a over 1 minus r, but I need that sum to be equal to 2 over x. So my goal here is to figure out, well, what is r going to be equal to in order for this to be the sum of my geometric series? So what I'm going to do is I'm going to manipulate this series algebraically so that this happens. The first thing I notice is I need a 1 minus a number in the denominator. So how am I going to get that 1 minus a number? Let's start with 2 over x. I know I need subtraction here, and I know I've got a 2 on top that I want to get rid of. So what I'm going to have to do is I'm going to need to add and subtract something down here to make this 0 out. So I could have a 2 and then a minus 2. I'm going to add 2 and subtract 2. Do y'all see how that doesn't change the value of the function y equals 2 over x? So then I could factor a 2 out of this denominator. So when I add 2 and subtract 2, I've got a net gain of 0 here. What I'm going to do is I'm going to group this x minus 2 together. Then what I want to do is I want to factor out a 2, or I'll distribute a 1/2. How about that? That's the same thing. Factoring out a 2 is the same thing as multiplying both the numerator and the denominator by 1/2, because that will give me a 1 in the numerator and also give me a 1 right here. So when I multiply 2 times 1/2, I'm going to get 1. And when I multiply 2 times 1/2 down here, I get 1 plus, and then I'm left with x minus 2 over 2 right here. Now this I could also rewrite as 1 over 1 minus, and then I've got x minus 2 over 2, but make this a negative, minus a negative. So I've got 1 over 1 minus a negative, x minus 2 over 2. I wrote it in this form so that you can see what a and what r are going to be equal to, so that it's in this form. So it looks like this I could write as a geometric series where a is equal to 1 because that's in the position of a right here. And then r would be equal to negative x minus 2 over 2 raised to a power of n. Do you see how the terms of this series, or this geometric series, would actually be equal to this right here? And because I used algebra to manipulate what we started with, this would be 2 over x. We can double check it just by going through the process of finding the sum, where a is equal to 1, r is equal to negative x minus 2 over 2. If I distribute the negative, that would be 1 over 1 plus x minus 2 over 2. To get rid of the complex fraction, I would then multiply both the numerator and the denominator by 2, and that would give me 2 over 2 plus x minus 2, and that's equal to 2 over x. So the sum of this geometric series would actually be equal to this function. So the polynomial terms, I would have an alternating series because r is negative. So when I'm raising a negative to an even power, I get a positive term. So when n is equal to 0, I would get 1. When n is equal to 1, I would get this negative term. When n is equal to 2, I would get this positive term, so forth and so on. So that's what this series would converge to. Now, to find the interval of convergence here, what I would need to do is set the absolute value of r less than 1. The absolute value of a negative is a positive. So what I would do is I would solve x minus 2 over 2 is less than 1 or greater than negative 1. When you're solving an absolute value inequality, if you have a less than there, the way you remove the absolute values is you take what's inside the absolute values and put it in between a negative bound and a positive bound. Let me take a step back and remind you guys of some algebra, because sometimes this gets a little fuzzy for Cal 2 students because it's been probably years since you've looked at absolute value inequalities. So if this is a number line, I've got 0 right here, 1, 2, 3, 1, 2, 3. If I wanted to graph the absolute value equation, absolute value of x equals 2, there's two numbers that would make this true. 2 and negative 2. If I said the absolute value of x is less than or equal to 2, would 0 be in there in the solution set? Is 0 less than 2? Yes. What about positive 1? What about 1.1, 1.5, 1.9, 2? What about 3? No. I mean, because I put an equal sign in this inequality, I'm going to use brackets here. What about negative 1? Is negative 1 a solution to this absolute value inequality? Sure it is. The absolute value of negative 1 is 1, and 1 is less than 2. So this works all the way up until negative 2. So when you have the absolute value with a less than, what you're going to do to remove that absolute value equation, or that absolute value function, is you're going to take what's inside the absolute value sign and sandwich it between a positive number and a negative number, and it's going to be whatever that number was over here. All right, so I'm going to erase this. I don't want this in my notes. And to get the domain of this infinite series right here, what I'm going to do is I'm going to solve this inequality for x, because that's what I got by taking the absolute value of r is less than 1. So to solve this absolute value inequality, the first thing I do is I'm going to multiply all three parts by 2. And negative 1 times 2 is negative 2 is less than x minus 2 is less than 2. And then to get the x by itself in the middle, I'm going to add 2 to all three parts. What you do to one part, you have to do to the other. And that's going to give us 0 is less than x is less than 4. So we would call this the interval of convergence for our series. So the infinite series that would represent the function y equals 2 over x is going to be this series, and the interval of convergence for that series is going to go from 0 to 4. Where is this series centered? The series is centered at x equals 2, because I said if we had x minus a number raised to a power, then that's where the series is centered. Now you can manipulate this series algebraically using properties of exponents to rewrite it as negative 1/2 raised to the n times x minus 2 raised to the n. And if you write your series like this, it may be a little easier to see where the series is centered. If you understand, or if you remember the geometric series, what it looks like and what the sum is equal to, you can algebraically manipulate your rational function to figure out what r is equal to when a is equal to 1, and then use the sum of your geometric series to find your infinite series. Theorem 18 is the convergence theorem for power series. It says if the power series converges at x equals c, where c is not equal to 0, then it converges absolutely for all x within that distance of c, from negative c to c. If the series diverges at x equals d, then it diverges for all x that are beyond that d. This part of the inequality means that if your series converges at x equals c, where c is not equal to 0, then it converges absolutely everywhere between negative c and c. If the series diverges, we have an absolute value with a greater than there, it's going to diverge for every value that's greater than d. So if this was a d here and our series diverged, at this point d, our absolute value of x greater than d would be represented by this region right here that I have shaded in green. So if your series converges at some point, it's going to converge everywhere in between the negative c and c. If it diverges, it will diverge from d to infinity and also from negative infinity to negative d. The corollary to Theorem 18 says the convergence of the series is described by one of the following three cases. There is a positive number r such that the series diverges for x with the absolute value of x greater than r. Notice the greater than, that's our divergence. But it converges absolutely for x with x minus a less than r. R is called the radius of convergence. The series may or may not converge at either of the endpoints. We won't know about these endpoints. These endpoints here are going to have to be checked. The series converges absolutely for every x, meaning the radius of convergence is all real numbers, or the series converges only at x equals a and diverges everywhere else. So what this means is we could have an interval of convergence, we could have an infinite interval of convergence that's all real numbers, or our series could converge only at the point where it's centered. Because notice when we looked at these graphs of these power series, every single one of these polynomials passed through the point wherever the series was centered. This series was centered at x equals 2. All of our graphs passed through that point. Our series converged at that point. This series was centered at x equals 0. All of our polynomials, even up to the 8th degree polynomial, passed through that point. So in plain English, what that means is you're going to have a radius of convergence that's going to be a finite number, infinity, or 0. This would be a graph that represents this first case. If we have a series that's centered at a, then there's going to be a range of values where this series will converge that goes from a minus r to a plus r. So here we would say our radius of convergence would go from a minus r to a plus r. If our series is centered at a and r is equal to infinity, then our interval of convergence would go from negative infinity to infinity, because a minus infinity is negative infinity and a plus infinity is equal to infinity. And the third thing that can happen is that if we have a series centered at a, if our radius of convergence is equal to 0, then we don't have an interval of convergence, we have a point of convergence. We would say that the series converges only at that point. How to test a power series for convergence. We're going to use the ratio test or the root test to find the interval where the series converges absolutely. Remember, we said ratio test and root test both were absolute convergence. If your series converged using either one of those tests, that showed absolute convergence. If the interval of absolute convergence is finite, we test for the convergence or divergence at each of the endpoints. This did not tell us what happened at the endpoints. We would have to check the endpoints. If the interval of absolute convergence is a finite interval or an open interval, the series diverges for x's beyond our radius of convergence. It does not even converge conditionally because the nth term does not approach 0 for those values of x. Now, if we use the ratio test, this is going to converge if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. This is the condition that's necessary in order for the ratio test to converge. It's the same condition that we're going to use for the root test. So let's look at example 1 here. Since I want to use the ratio test, I'm going to start by identifying what a sub n is and what a sub n plus 1 is. So a sub n is going to be negative 1 to the n times 8x plus 6 to the n. A sub n plus 1 is going to be this, and we can simplify that by saying that that's going to be negative 1 times, this is still going to be negative 1 to the n plus 1, but because with the ratio test we use the absolute value, I'm not terribly concerned about that negative. And this would be 8x plus 6 to the n times 8x plus 6 to the first. So when I do the ratio test, I'm going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Because of the absolute values, I'm going to ignore those negative 1's raised to a power. So I'm looking at the n plus 1 term divided by the a sub n term, and these terms are going to cancel out, leaving us the limit as n approaches infinity of absolute value of 8x plus 6 is less than 1, because that's where this series is going to converge absolutely. Notice there's no n left here. What's the limit as n goes to infinity of something that doesn't have an n in it? It's just that thing, right? So that means that this series is going to converge absolutely, provided that this inequality holds. In order to solve that inequality for x, I'm going to set up a compound inequality that goes from negative 1 is less than 8x plus 6 is less than 1. To get the x by itself in the middle, I'm going to subtract 6 from all three parts, and that's going to give me negative 7 is less than 8x is less than negative 5. And then I divide all three parts by 8, and I don't have to flip the inequality because I'm dividing by a positive number. And that gives me the interval of convergence is going to be the interval that goes from negative 7/8 to negative 5/8. Just to help you get an idea of this, here's a number line. Negative 7/8 is this number right here. Negative 5/8 is this number right here. This would be our interval of convergence. Where is this series centered? It's centered right here at 6/8, is it not? Well, 6/8 reduces to 3/4. And you say, well, that doesn't look like the form that you told us. You said it needed to look like this to see where it's centered. Well, can you algebraically manipulate this so that you have a 1 as a leading coefficient here? Sure you can. This would be adding a negative 6, and then to get the a by itself, you divide by 8, and guess what you get? You get a negative 6/8. This is a series centered at negative 6/8. What would be the radius of convergence then, looking at this graph? Because we're asked to find the series, radius, and interval of convergence. The radius of convergence is this distance right here. It's the same distance from where it's centered. It's centered at negative 6/8 or negative 3/4. How far out did I go to get the numbers on these endpoints here? 1/8. So my radius of convergence here is going to be 1/8. The series is centered at negative 3/4 because 6/8 reduces to 3/4. For what values of x does the series converge absolutely? These are the values of x where the series converges absolutely. This would be my answer for B. It converges absolutely from negative 7/8 to negative 5/8. And then we want to check for what values of x does the series converge conditionally. To determine conditional convergence, you have to check convergence at the endpoints, because that corollary guaranteed us convergence on these range of values, but it didn't tell us anything about the endpoints, which is why we used an open parentheses here when we did this step. So that means that you need to check the convergence at the endpoints. I'm going to check the convergence here of this series from n equals 0 to infinity of negative 1 to the n. In place of x, I'm going to plug in a negative 7/8 raised to the n. And then I've also got to check the convergence of this series when I plug in a negative 5/8. So when I plug in a negative 7/8, the 8's are going to cancel out. That gives me negative 7 plus 6 is negative 1. So that's negative 1 to the n times negative 1 to the n. That's going to be the infinite series of 1. That's going to be infinity. That series diverges. So I don't include convergence at negative 7/8. Then I'm going to check the convergence of the series when I plug in a negative 5/8 in place of x. So that's going to give us negative 1 times 8 times negative 5/8 plus 6 raised to a power of n. Well, negative 5/8 times 8 is -5, plus 1 is 1. 1 raised to any power is that power, and this is going to be -1 to the n. So this is going to oscillate between -1 and 1, this series will, if I were expanding out these terms, and that also diverges. So we don't have any points where the series converges conditionally. If either one of these series would have converged, that would have been where the series converged conditionally. But because both of these endpoints diverges, we don't have to worry about that. Our series converges absolutely on this interval, and that is all. It doesn't converge conditionally anywhere. In example 2, we're going to consider this series. Notice this looks a lot like a geometric series, doesn't it? And a geometric series converges if the absolute value of r is less than 1. Furthermore, it converges absolutely where the absolute value of r is less than 1. So what I'm going to do is I'm going to treat this, instead of using the ratio test or the root test, I'm going to use the geometric series test. So this is going to converge if the absolute value of x plus 5 is less than 1. So I'm going to set up my compound inequality, and I'm going to solve this for x by subtracting 5 from all three parts. And when I do that, that gives me -6 is less than x is less than -4. This gives me the interval where the series converges absolutely. This would be the answer for part B. Where is this series centered? It's centered at -5. So here's -5, and then it goes from -6 to -4. So if I were to graph where this series converges absolutely, it's easy to see where this series is centered. It's centered at -5. And what would the radius of convergence be? The radius of convergence is 1. The series converges absolutely for x's between -6 and -4. We know because it's a geometric series that it's going to diverge anytime this is greater than or equal to 1. So it's not going to converge conditionally anywhere. If a series converges conditionally, it will be at the endpoint. So for this one, there's no need really to check the endpoints, but we can go ahead and check them just to show you what I'm talking about. So if x is equal to -6, we would have the series -6 plus 5 raised to a power of n, and that would just be -1 raised to a power of n, with the terms of the series alternate between -1 and 1. It oscillates, so this series diverges. And if x is equal to -4, we would have the series n equals 0 to infinity of -4 plus 5 raised to a power of n, and that's just the series n equals 0 to infinity of 1 raised to a power of n, and that's equal to infinity, so it also diverges. So the series does not converge conditionally anywhere. It converges absolutely on this range of values. So sometimes if your problem is set up, you can use the geometric series or you can use the ratio test. In this next example, this is not set up so we could use the geometric series. I don't have anything that I could write as r raised to a power of n. I have to use the ratio test because it's not a geometric series. So because it's not a geometric series, we're going to use the ratio test. In order to use the ratio test, I need to identify what a sub n and a sub n plus 1 are. So a sub n is the argument of our series. A sub n plus 1, we replace n with n plus 1. And then simplify this. This will be 3x minus 2 to the n times 3x minus 2 divided by n plus 1. For the ratio test, we look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. This is going to be the limit as n approaches infinity of the absolute value of my n plus 1 term. And then dividing by a sub n is the same thing as multiplying by the reciprocal of a sub n. And then we see what terms will cancel out. So the 3x minus 2 to the n will cancel here. And that's going to give us the limit as n approaches infinity of the absolute value of 3x plus 2 times n over n plus 1. For this limit, the variable is n. And since the degree of the numerator is the same as the degree of the denominator, this is going to be the absolute value of 3x plus 2 times 1, because n over n plus 1 as n goes to infinity is equal to 1. That converges as long as that is less than 1. I'm going to use this now to set up my compound inequality to get the domain for x. Somehow I changed that minus 2 to a plus 2. This should be a minus 2 right here. this will be a minus 2 right here as well. All right, so I'm going to set up my compound inequality as -1 is less than 3x minus 2 is less than 1, and then solve this for x. So when I add 2 to all three sections of this compound inequality, I'm going to get 1 is less than 3x is less than 3. And then we divide all three parts by 3, and we get 1/3 is less than x is less than 1. This is where the series converges absolutely. If I were to graph this, it would be the interval that goes from 1/3 to 1. Where is this series centered? It's centered at x equals 2/3. What is the radius of convergence? The radius of convergence is 1/3 because the series is centered at 2/3, and the distance from 2/3 to 1 is 1/3, and the distance from 1/3 to 2/3 is also 1/3. Now we need to check the convergence of the endpoints. So if x is equal to 1/3, our series becomes, we're just going to plug in a 1/3 in place of x in our series. So this series becomes the series n equals 0 to infinity of -1 to the n over n. And what do we know about this series? We worked with it about a week ago. So this is a convergent alternating series. That means that our series converges conditionally at x equals 1/3. And what happens if x is equal to 1? We replace x with 1 and then simplify. 3 minus 2 is 1. 1 raised to a power of n is 1. So this is going to be 1 over n. And we know that this is a divergent p-series. So our series converges absolutely from 1/3 to 1, not including the 1. But the interval of convergence for this series is the interval that goes from 1/3 to 1, including the 1/3, but not including the 1. That would be the domain for this infinite series, the domain for x. Let's look at this series. We're going to use the ratio test because clearly this doesn't fit the geometric series. So for the ratio test, we need to identify a sub n. Well, that's going to be 3 to the n, x to the n over n factorial. And we also need to identify a sub n plus 1. And that's 3 to the n plus 1 times x to the n plus 1 over n plus 1 factorial, which can be rewritten as 3 to the n times 3 times x to the n times x over n plus 1 times n factorial. So using the ratio test, we've got the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n, but dividing by a sub n is the same thing as multiplying by the reciprocal, so that's going to give us n factorial over 3 to the n x to the n. And we cancel where we can. The 3 to the n's cancel, the x to the n's cancel, the n factorials cancel, and we're left with the limit as n approaches infinity of 3x over n plus 1. And as n goes to infinity, that's going to give us the absolute value of 3x over infinity, isn't it? Because there's no n's. We're plugging in the infinity in place of n. X is a variable. According to the ratio test, this converges as long as that is less than 1. So we can set up our compound inequality. -1 is less than 3x is less than 1. 3x over infinity. I'm going to use some sloppy notation here. In order to get rid of this infinity in the denominator, I'm going to multiply all three parts by infinity. And -1 times infinity is negative infinity, and 1 times infinity is infinity. And then if we divide by 3, negative infinity divided by 3 is still negative infinity, and infinity divided by 3 is still infinity. So this is where our series converges absolutely. That means that our radius of convergence is equal to infinity. So when you do the ratio test, you can identify that your radius of convergence is infinity if you get an infinity in the denominator after you evaluate your limit. If we would have had an infinity in the numerator, then we would have had 0 right here. You didn't have to do this step per se. You could have just said, okay, well, let's multiply by infinity, and we get the absolute value of 3x is less than infinity. And then you could have said, okay, the radius of convergence is infinity, and the interval of convergence is all real numbers. The comment was, if we're dividing by infinity, I thought the limit was 0. And if all I was doing was evaluating the limit, I would agree with you. Yes, this limit is actually equal to 0. But whenever we're trying to find the domain for the interval of convergence, I'm going to take what I get and set this less than 1. That's the condition for the convergence of the ratio test. So I left the infinity in my limit once I evaluated that limit so that I could set up my inequality and solve for x. Get the x by itself in the middle to figure out what the radius of convergence is and the interval of convergence. We're using the ratio test from earlier in chapter 10 and applying it in a different way to find this interval of convergence for a series, an infinite series. If all I was doing was evaluating the limit, then I would say, yes, this is equal to 0 and the series converges absolutely. I've added this problem. It's from your homework. It's problem number 25 because I didn't put an example in my notes that looks like this. So consider the series n equals 1 to infinity of n to the n, x to the n. I don't want to use the ratio test for this one since both of these are raised to the power of n. We're going to use the root test. And remember, from the root test, we have this. Using the root test, we take the nth root of a sub n, and if that limit is less than 1, then the series is going to converge. So we're going to look at the limit as n approaches infinity of the nth root of, I can write this as n times x raised to a power of n. And the nth root of this raised to the n is just the limit as n goes to infinity of n times x. And it's going to be the absolute value of this. So this is going to be equal to infinity times the absolute value of x. And this will converge if that's less than 1. So to set up my inequality, I'm going to look at -1 is less than infinity times x is less than 1. To get the x by itself in the middle, we're going to divide all three parts by infinity. And that's going to give us 0 is less than x is less than 0, which means that our radius of convergence is equal to 0. And there is no interval of convergence. It converges only at x equals a. Where is this centered? The series is centered at 0, and so this series converges only at x equals 0. So this is what it would look like if we use the root test to determine the radius and the interval of convergence. This is the condition in order for this series to converge. So once I evaluate the limit, I use that, force that to be less than 1, and I use that to set up my compound inequality. And I end up with zeros on both ends, which means that the radius of convergence is 0, and this series converges only at that point. Well, what happened was when we evaluated the limits, if we have the infinity on top, our radius of convergence is 0, and it converges only at the point. But if our infinity is in the bottom, our radius of convergence ends up being infinity, and the interval of convergence is all real numbers. Now, we can perform operations on power series because when we expand the power series, they just end up being infinite polynomials. We need to be able to find what the domain of the power series is going to be if we combine power series. So on the intersection of their intervals of convergence, two power series can be added and subtracted term by term, just like the series of constants. They can be multiplied just as we multiply polynomials, but we often limit the computation of the product to just the first few terms because we have to use FOIL or distributive property for multiplication. The following results gives a formula for the coefficients of the product, but we omit the proof because it's really cumbersome. So if you are multiplying two series together, we have a of x and b of x being equal to two infinite power series, and they will converge absolutely for the absolute value of x is less than the radius of convergence. And the way you come up with c sub n is this, where k is equal to 0 to infinity. I don't think I'm going to ask you to do any of these problems because this is quite cumbersome. Definitely won't ask it on a test, but I don't think I even asked it on the homework. Theorem 20 says that if we have an infinite series that converges absolutely, then any function of that power series will also converge absolutely for any continuous function f that's on absolute value of f of x less than r over that range. Theorem 21 is the term-by-term differentiation theorem. It says if we have an infinite power series that has a radius of convergence r that's greater than 0, it defines a function on this open interval. That's how we came up with these numbers. We got these bounds for our interval of convergence. This function has derivatives of all orders inside the interval, and we obtain the derivatives by differentiating the original series term by term. If you're trying to find the derivative of a series with respect to x, X, remember, is the variable for the derivative. Everything else is a constant, and we treat it as if it were a constant. So for example, if I have y equals ax to the n, when I take the derivative of this, that a is a constant. I leave it there, and I'm going to bring that power down front and then subtract 1 from the exponent. So if I have y equals a series ax to the n, when I take the derivative of that series, or I'll tell you what, if I expand that series, that would give me a plus ax to the first plus ax to the second plus ax to the third, so forth and so on. If I were to take the derivative of that, when I take the derivative of this first term that I got when n was equal to 0, when I take the derivative of a constant, I get 0. When I take the derivative of a times x, I would get a. When I take the derivative of a times x squared, I would get 2ax. When I take the derivative of ax to the third, I would get 3ax squared. Agreed? Well, what happens here is instead of this starting at 0, when I take the derivative, we're going to start at 1, because what happened to the term when n was equal to 0? Well, it became 0. So when n is equal to 1, I get a, and then I multiply times n, and then this is going to be x to the n minus 1. Notice when n is equal to 1 here, I get a times 1, x to the 0. Well, that's a. When n is equal to 2, I get a times 2, x to the 2 minus 1 is x. That's this term. So when you take the derivative of a series and you don't want to expand it out, every time you take the derivative, you've got to add 1 to your starting point because your constant term is going to go to 0. What would the second derivative be? I'm not going to expand it out. I just want to know what the second derivative is going to be. What am I going to start in at now? If the function starts at 0, the first derivative starts at 1, where's the second derivative going to start? At 2. And then I'm going to multiply these constants times that power. I bring the power down front, so that gives me a times n minus 1, x raised to the, and then we subtract 1 from that exponent, and that gives us n minus 2. What would my third derivative be? What would I start my series at? 3. And these constants stay there, and then I bring that power down front using the power rule for derivatives, and then subtract 1 from that exponent, and this would be the third derivative. So do you see how easy it is to take derivatives of power series? If this series converged on the interval from a minus r to a plus r, so does this one and this one and this one. So remember, when you take the derivative, you've got to subtract 1 from the exponent, bring down the exponent, but you've also got to start your lower limit at 1 more than what the previous one was. Now when we integrate, we're going to integrate a term at a time. And it's going to be similar to what we just did with the derivative. Let's just look at example 5. It says the series e to the x equals this. I'm telling you that's what it's equal to. This converges to e to the x for all x. If I were to write this using sigma notation, what would it look like? Wouldn't this be x to the n divided by n factorial? You need to know that by definition, 0 factorial is equal to 1. That's by definition. So here's our series. Part A asks us to find a series for the derivative with respect to x of e to the x. Knowing what we just did, we're going to take the derivative with respect to x of e to the x. We know that that's equal to the derivative of each one of these terms. Let's just write them down. What's the derivative of 1? I'm just looking at these terms right here. I'm taking the derivative a term at a time. If e to the x is equal to this, when I take the derivative of e to the x, I'm going to take the derivative of, I'm going to look at the expanded series. That's 1 plus x squared over 2 factorial, x cubed over 3 factorial, and I'll just carry it out that far. So the derivative with respect to x is equal to the derivative of a constant is 0. The derivative of x is 1. The derivative of x squared divided by 2 factorial, well, that's going to be 2x over, and 2 factorial is just 2 times 1, isn't it? Plus for 3 factorial, the derivative, that would be 3x squared. Bring the constant down front, subtract 1 from the exponent. 3 factorial is 3 times 2 times 1, and we'll let that go. Now let's simplify this and see what we get. I don't need the 0. I get the 1. And then these 2's are going to cancel out, and that's just going to give me x. These 3's are going to cancel out and give me x squared over 2 factorial. And if I would have kept going, the next term would have been x cubed over 3 factorial, so forth and so on. And guess what that's equal to? That's equal to this series expansion over here. That's just e to the x. Well, the derivative of e to the x is e to the x, so this works. If I wanted to write this as a series, I wouldn't need to start this at n equals 1. I could start it at n equals 0. It's going to be x to the n over n factorial. And because this series converged everywhere, so will this series. We were told this converges for all x, so the domain goes from negative infinity to infinity. All right, let's look at what happens for part B. So on part B, we're asked to integrate e to the x. Well, that means I'm going to integrate this infinite series with respect to x. So we're going to integrate this a term at a time. What do you get when you integrate 1? You get x. What do you get when you integrate x? You get 1/2 x squared. What do I get when I integrate x squared? Well, we're going to add 1 to the exponent, divide by the new exponent. And when I integrate x cubed, I'm going to add 1 to the exponent, divide by the new exponent. And when I integrate x to the 4th, I'm going to add 1 to the exponent, divide by the new exponent, but there's a constant of 4 factorial down there already, and leave that alone. So since there's no bounds on this integral, I've also got to put plus c. Well, cleaning this up, that's going to give me x plus, I could write this term as x squared over 2 times 1 is 2 factorial, plus x cubed over 3 times 2 factorial is 3 factorial, x to the 4th over 4 factorial, x to the 5th over 5 factorial, and this looks an awful lot like e to the x, doesn't it? Where this arbitrary constant here takes the place of that 1. So this is e to the x plus c. And I'm not going to take the time to go through part C because we're running out of class time, but we could replace x with negative x in the terms for the series, and then find the series that converges to e to the negative x for all x, and then multiply that. And if we multiply e to the negative x times e to the x, we would get e to the 0, which is 1. I've run out of time, so I'm not going to have time to do part C, but I did want to show you how to take the derivative of a series that's expanded, or you can take the derivative of the terms using the sigma notation. And that will wrap up section 10.7.